The first issue we investigate is the equivalence of different utility functions. We recall that the reasoning, and therefore the play of a player, is driven by the utility function. Obviously, players sharing the same utility function will behave similarly. The question we pose is whether, every time two players have different utility function, they will exhibit a different behavior. Consider the example in the picture. We have a two-player normal form game in which every player has two actions. Consider now another game that is the same of the previous one, except for the utility of player 1. In the right game, player 1 has a utility of 5 for the outcome corresponding to the action profile A2, A4. Instead, in the left game, player 1 has a utility of 2. So the difference between the two games is only for a single payoff of player 1. However, if we focus on the preferences of player 1 on the outcomes, we have that for both games, the left and the right ones, the outcome A2, A4 is strictly better than A1, A3, that is, in its turn, strictly better than the other two outcomes. Player 1 is indifferent on these last two outcomes. As I said before, the reasoning of the players depend on their preferences. If they have the same preferences, their reasoning is the same. Therefore, we can expect the same solution to both games. However, as we will see later, this is true when focusing only on pure strategies. So, when focusing on pure strategies, every transformation of the utility function of player I, such that the preference ordering over the outcomes is preserved, leads to a utility function that is equivalent for that player. Again, this holds when focusing on pure strategies. We now consider the case with mixed strategies. Suppose that the mixed strategy of player 2 is that one in the picture, that is 3/4 over action A3 and 1/3 over action A4. The expected utility of player 1, provided by taking actions A1 and action A2, are those reported in the picture. In the first left game, A1 gives a utility of 3/4 and A2 gives a utility of 1/2. In the second right game, A1 gives a utility of 3/4 and action A2 gives a utility of 5/4. It is easy to see that player 1 has, in the two games, different preferences over her actions. In the left game, player 1 prefers strictly A1 rather than A2. In the right game, instead, player 1 strictly prefers action A2 rather than action A1. So, the preferences over the lotteries are different in the two games. This shows that the two games are not equivalent, and that the behavior of player 1 may be different in the two games. We ask when we have this equivalence between utility functions, in the case the players can reason in mixed strategies. We have that every affine transformation of the utility function of a player, where the parameter A is strictly positive, leads to a utility function that is equivalent for that player. That is, the equivalence is possible only when an affine transformation is applied with A strictly positive. Notice that, given a game, we can apply different affine transformations to each player, obtaining thus a game that is equivalent to the original one. Now we focus on two-player zero-sum games. They are two-player games in which, for each outcome, the sum of the utilities of the players is 0. In the picture, we have the rock, paper, scissors game. On the right, we have the space of the utilities of the player. In the x-axis, we have the expected utility of player 1, while in the y-axis, we have the expected utility of player 2. Initially, we focus on the outcomes. We report in the utility space the outcome -1, 1. Now the outcome 0, 0. And finally, the outcome 1, -1. Now we focus on the lotteries over the outcomes. Any possible lottery between the two outcomes marked in red correspond to the line connecting the two outcomes in the utility space. The same for these two outcomes. The image of strategy profiles in the expected utility space is the line reported in the picture. Consider this game. The peculiarity is that for every outcome, the sum of the utilities of the players is 3. Games such as this one are called constant sum game. The image of the strategy profiles in the utility space is obviously a line whose slope -1. Exactly as in the case of the zero-sum game, the difference is that the line does not cross the origin in 0, 0. It can be easily seen that a two-player constant game is equivalent to a zero-sum game thanks to an affine transformation. Geometrically, we just need to translate the image of a zero-sum game. A more general class, in the case of two-player games, is composed of two-player strictly competitive games. A two-player game is called strictly competitive when, moving from any possible strategy profile, if the expected utility of a player increases, the expected utility of the opponent reduces. So we cannot find any direction along which the utilities of both players increase or decrease. By definition of a two-player strictly competitive game, the image of the strategy profiles in the utility space must be a curve monotonically decreasing. Otherwise, there is a direction along which the utilities of both players increase. In the picture, there is a simple example of monotonically decreasing curve. Obviously, if the image included an area, there will be points from which both players can improve their utility, and therefore the image must be a curve. Again, if the curve is not monotonically decreasing, both players can improve their utility from some points. In addition, let us notice that the image cannot be discontinuous, since the strategy profile space is a compact set and the utility function is a continuous function. The main result is that in two-player strictly competitive games, the image of the strategy profiles in the expected utility space cannot have any shape. It must be a line with a strictly negative slope. Therefore, by means of an affine transformation, it is equivalent to a zero-sum game. The proof is very simple and it is based on geometrical arguments. Consider a generic two-player game with 2 actions per player. The reasoning can be easily extended to games with more actions. Consider a utility space and report the vectors of payoffs of the outcomes. Consider the pair of outcomes A and B. Any lottery between A and B is possible, and therefore the line connecting A to B is part of the image. Consider the outcomes A and C. As before, any lottery is possible, and therefore the line connecting A to C is part of the image. The same holds for B and D, and for C and D. The polygon defined by A, B, C, D must not have an interior for the arguments discussed before. Thus, we need that 2 pairs of edges must overlap, as in the figure. However, this is not sufficient. Indeed, if we consider the uniform mixed strategies, we have that there exists always a point that is strictly better or strictly worse than B in the figure, unless A, B, C are on a line. So, with two players, zero-sum games are equivalent to constant-sum games that are equivalent to strictly competitive games. We focus now on Bayesian games. Start with a simple two-player game with two actions per player reported in the picture. It is commonly called Battle of Sexes, where player 1, usually a male, can decide on two possible concerts, Bach or Stravinsky. The same for player 2, usually the female. Notice that the utilities in the game are such that both players prefer to attend to a concert together rather than alone, but they have different preferences on which concert to attend to. Suppose that the utility, and therefore the preferences, of player 2 is not known to player 1. Suppose that two cases are possible. The first case is the previous case, that is the game on the left. While in the second case, the female prefers to attend to a concert alone rather than with player 1. The utilities of player 1 are the same in both cases, while the utilities of player 2 are different. Technically speaking, we say that player 2 can be of two different types, that we denote with theta 2.1 and theta 2.2. Associated with the types, we have the probabilities that such types occur. They are denoted with omega 2. The same can happen for player 1. That is, player 1 can be of two different types, theta 1.1 and theta 1.2, each associated with a given probability. The representation of the Bayesian game, in which we have types, probabilities, and different utility matrices for each combination of types, is called epistemic. However, a Bayesian game can be represented as an extensive form game in which the nature player initially chooses the types of the player. Then we can encode each single game in which the types are fixed in the game tree. Here the case of the first game, here the case of the second, here the case of the third, and here finally the case of the third. So any possible Bayesian game is essentially an extensive form game with nature, and therefore it does not require any further additional model to capture the situation.